Hello guys, this is CodeNCode and this is an editorial for the problem feasible relation taken from HackerEarth. So the problem is, I'm not going to explain the problem statement directly. The example task case, it is easy to understand problem but not to solve. So the problem is you are given n and k, n and k, and n indicates number of variables and k indicates number of relation between them. There are two kind of relation between variable, either they are equal and they are not equal, and you have to tell whether the given set of uh, k relation is feasible or not. What I mean is that take a look at the first test case. It says 2 indicating that there are two uh, variables and two relation between them. First relation is variable 1 is equals to variable 2. This is possible, and then in the second line it says variable 1 is not equal to variable 2. Now this is a contradiction. Now suppose variable 1 is x and variable 2 is y. So in first statement it is saying that x is equal to y, and in the second statement it says x is not equal to y. So this set of condition is actually not feasible because either x can be equal to y and either x cannot be equal to y. That is why the uh, the conditions that are given, the set of conditions, are not feasible. That is why we are printing no. In the second test case, we are having three variables and two conditions. So variable 1 is equals to variable 2, that's okay. Variable 2 is not equal to variable 3, that is again okay. So this set of condition is actually feasible because this is possible to give values to variables such that both the condition follow. Since variable 1 is equals to variable 2, I can give variable 1 and 2 value 10, while 2 is not equal to 3. So you can give variable 3 value like 20. So 1 is equals to 2 because both are 10, but 2 is not equal to 3 because 2 is 10 and 3 is 20, so they are not equal. So these two the last set of conditions, like these two conditions, are feasible because this is possible to give values to variables such that they follow both the condition given, all the key condition basically. That is why we are printing yes. Now the question is how you can solve this problem. Since this video editorial is in the graph theory list, so it is 100% sure that the problem is going to be solved using graph theory. Just think how you can solve it using graph theory. So I've taken two more test cases from myself. So there are 5 variables, 5 relation among them. So 1 is equals to 2 and 3 is equals to 1. So variable 1 is equals to variable 2 and variable 3 is equals to variable 1. So basically 1 is equals to 2 is equals to 3. So you can put 1, 2 and 3 in the same set, right? Just ignore for the moment 4 is equals to 4 is not equal to 2. Consider this statement 5 is equals to 4. So 5 and 4 are in the same set. So 5 and 4 are in the same set, and 1, 2 and 3 are in the same set, right? Now let's start considering these two. So it says 4 is not equal to 2. Now 4 and 2 actually lie in two different sets, right? Because 1, 2, 3 lie in the same set, which means they all are having the same values. So you can give set 1 value and set 2 another value. So this condition will follow because 4 and 2 are in different sets. Now 3 is not equal to 5. Again 5 is in the second set while 3 is in the first set. So again they both lie in the different set. So we can still this condition can hold because they are in the different sets. So different sets can be given different values, but same but two elements which lie in the same set can't be given two different values. So since these two conditions can hold, hence the answer of this is yes, because these conditions are feasible while this is not, because 1 and 2 are in the same set and 1 and 3 are in the same set, which indicates 1, 2 and 3 are in the same set. Basically 1, 2 and 3 are equal, but this condition says this line says that 2 and 3 are not equal, which is contradiction because 2 and 3 are equal. That is why these conditions are not feasible. That is why we are printing no. So if I show them graphically, so what we are going to do, we are going to create a graph using equal sign. So if two variables are having equal sign between them, that would indicate that these two variables, uh, these first of all the variables we would consider as nodes, and equal sign we would consider as edges. So for this task case, there is an edge that 1 is equals to 2, so 1 is connected to 2, so there is an edge between 1 and 2. 3 is connected to 1, so there is an edge between variable 3 and 1. Then 4 is not equal to 2, save it for later, because what we are going to do, we first we would create the complete graph and then check whether they lie in the same connected component or different connected component. So we will save it for later. And then 5 is equals to 4, which means there is an edge between node 5 and 4. And now since all edges are added, now we would go for not equal to condition. Sorry, so it says 4 is not equal to 2, so 4 and 2 lie in two different connected components. So this condition will hold because it says 4 and 2 should not be equal to each other. That's okay because this connected component, all the elements in this connected component are equal to each other. Basically they represent a single set. So all these elements can be given a single value like 50, say. So 1 is equals to 50, 2 is equals to 50, 3 is equals to 50. What this says that 4 should not be equal to 2. So that's okay because for this connected component we have given the value 50. So all these elements, all these variables will have value 50. And for the second connected component we can give any number like 100. So 4 is having a value 100. So we can see that 4 is not equal to 2 because 2 is 50 and 4 is 100. So all the elements in a single connected component are same. That is why they are in the same connected component. And all the elements which are in different connected component can be different. Now the last condition says 3 is not equal to 5. We can again see they are in the different connected components, so this condition again holds. So what we would do, we would create a graph using the equal sign would indicate that there is an edge, and the not equal signs, for the not equal signs edges we would save them to check later whether these two nodes lie in the same connected component or not. If they lie in the different connected component, then answer is okay, otherwise the answer is no. So this is the problem. Let me increase the font size. So the problem is feasible relation from HackerEarth, and it says there are n and k can be as large as 10 power 6 and there are 10 test cases. So let's jump into the editor, control and start coding. This should be visible to you now. The first thing, if you remember, for just a moment, the first thing, if you remember, in our from our graph theory videos, what we do, we create a vector of int array. Since there are 10 power 6 nodes, so we are going to take 10 power 6 size of adjacency list would be 10 power 6, and then we would need visited array, again 10 power 6 size. And what do we need more? I don't think so we need anything else, so that's enough. Sorry, in t and k, a and b for edges. Now in each test case read n and k. After reading n and k, clear the adjacency list from the previous test case, because in the next test case adjacency list may contain input from the previous test case, so it is important to clear the list before taking input. And initialize the vector array again, visited array again to 0. Now after that, there is one more thing that we need, string to read the operator. Why? Because this would be given as a string, so we would be reading these as string. So now there are k inputs, so let's equals to k I plus plus scene a, because the in the input first would be a number, then would be a string, and then third would be another number. So a, and then I have taken op for operator, and then b. If operator is equals to equal, so if it is equal operator, what we have to do, we have to if operator is equal, then there is an edge between node a and b. So what we would do, we would, in the adjacency list of a, we would insert b, and in the adjacency list of b, we would insert a, else the operator is not equal to. So for that we have to save a and b to check for later. So that is why we need another vector, or basically a list where we can save the pairs, because we have to save pairs. So in C++ STL, that is standard template library, there is something called pair, where you can have a pair of let me write it here. So what it says, that p is a pair which have two values, first and second. First value is integer and second value is integer. So since we want to save, this is how you create a pair. Now variable p would have two values. First can be accessed like p dot first. You can access first value, basically x value, and second value can be accessed like this. So this is how you create a pair in C++, and this indicates the first value is going to be int and second value is going to be int. This is how you declare a pair. So since in the vector we are going to save pair, that is why we are in the template of vector, we are telling it that we are going to save pairs this time, and then the variable, let's call it edge list. Now since it is a not equal to sign in the else condition, so in the edge list we would insert this a and b. So what this curly brace does, when passed to what we call it, to integers, it would create a pair of integers, because in the edge list you can push back or insert only pairs. So there is a function to make pairs if of two integers like this. But in C++ 14, I guess, you have an option that instead of writing make pair, you can simply use curly braces and two integers or two variables, so it would create a pair of them. So this would form a pair, and then we can insert in the edge list the pair. So finally we have the edge list, and our graph is ready. Now you remember what we have to let me complete this thing first. So for I is equals to 0, I less than edge list I plus plus, sorry, edge list dot size I plus plus. Basically now we are going to just a second, we are traversing the edge list. Oh sorry, a and b we already are having, and what we are doing, we are taking edge list, just a second, dot second. Now A is equals to first element of the ith edge and B is equals to the second element of the ith edge. So now we are having A and B, and we have to test whether A and B lie in the same set, same connected component or not. Before that, take a bool flag and initialize it to be true, indicating the relation is feasible. So now if a connected component of A is equals to connected component of B, that is they both lie, this is not equal condition that variable A and variable B should not be uh, are not equal to each other, right? So they should not be in the same connected component. But what this says is that connected component of A and B are same. So in that condition, flag is false and simply break, because this contradicts this the relation, and hence it cannot be a feasible relation. That is why flag is set to false and we are breaking. And remember, this is the CC array. We will take a CC array, integer CC array, CC 10^6. So CC array contains the connected component in which each element belongs to. So since we need to know for the condition 4 is not equal to 2, we need to know which connected component does 2 belongs to and which connected component does 4 belongs to. If I call this whole connected component first, so this is first connected component and this is second connected component. So connected component of 2 is 1, connected component of 4 is 2. So 1 is not equal to 2, that is why they must be in the different connected component, and hence this condition is okay. So we must know for each node which connected component does it belongs to. So CC array would contain the same. So before we can actually use the connected component array, we must initialize the connected component array. So for that, we need to find all the connected component, and you know how we do this. Let me some space. So I is equals to 1, I less than equals to n, because there are n variables, I plus plus. If you remember from the finding connected component lecture, if visited of I, that is ith node is 0, is not visited, we make connected component call. But we also should have current connected component. This is current connected component number. Okay, for each test case, initialize current connected component to be 0. Now if ith node is not visited, that indicates ith node belongs to a new connected component. So current connected component plus plus, so initially it was 0, for the first connected component it would become 1, and then you would make a DFS call to ith node. This is how we used to find connected component, right? And if you have no idea, just go watch the connected component video in the graph theory list in node. So what we do when we reach, first thing we do is mark it visited. After that, the current component connected component number is saved into this. So if we are exploring the ith connected component, then current connected component value is equal to I. So for this node, we have to save then which connected component does it belongs to. So CC of this node is equals to current connected component, and for in child in the adjacency list of current node, if child is not visited, so if it is equals to 0, which indicates it is not visited, you would simply make a TFS call to the child, and that's all. After this, all nodes would have ready at CC of node, we would have its connected component number, to which connected component does it belong to. So now For A, I can check which connected component does it belong to, and for B, we can check which connected component does it belong to. If they lie in the same connected component and it says they should not be equal, but they are in the same connected component, hence they are not equal. That is why if this condition arises, then the relation is not feasible, and hence we are setting the flag to be false and breaking out of the loop. And finally, if flag is equals to true, or simply if flag, that means the same thing. If flag, that is if flag equals to true, then cout yes, else cout no. I hope we don't get any error. Let's call it as for now. Okay, just a second, let me remove this because in this video I don't need that one. Okay, it is running. Simply let's copy the code and directly let's run it into the compiler of HackerEarth itself. So it is compiling, and yep, the expected output was no and yes, and our output is no and yes. So sample test cases are passing. Now let's go for submission. Taking more time, yep, than usual, evaluating, and yep, accepted. So you see how this interesting problem can be solved using graph theory. So if you think that this was an interesting problem and you have learned something, leave a like or comment in the comment section. And I have also created an Instagram ID, so you can follow me there if you want, because I'll be keeping you guys updated about the videos or projects I'm currently working on. So thank you guys for watching, and if you have any suggestion, anything, let me know. And one more thing, of course, this channel needs your financial support, because you guys are my only support for now. So if you can, just go out and donate whatever you can. So thank you guys for watching, and yep, till the next video drops, keep coding. Thank you.